All right, so this is the Unit 6 test. Just doing a couple things for the TI video. Plug my thing in. So number one states, what's the function that represents the exponential function y equals 7 to the power of x after a stretch by a factor of 5? And a vertical shift up 2. So both of these are vertical. So let's go ahead and do that. So vertical stretch by a factor of 5 means we need to multiply 5 on the outside. We'll have f of x next. Whatever our function is goes next. And then we have a vertical shift up 2. So vertical shift up 2 means I need to do plus 2 on the outside. Now, if I look at f of x is the same as y. So my final answer is going to be 5 times 7 to the x plus 2. Usually when we wrote this, we did the parentheses like that, but that's it. That's all we want to do. So not really something to put into the calculator. You can if you want to double check, which that's why the video is here. So if we do want to double check it, we'll just do y equals 7 to the x. Oops. Let's get rid of these ones. All right, so we've got 7 to the power of x. And then for our y2, we have our shift, so 5 parentheses 7 to the power of x. It's wrong place. Okay. 5 parentheses 7 in parentheses to the power of x, and then plus 2. So if we graph this, I hit zoom in 6. I don't think my window is normal. So we can see the red one is definitely going to be up 2 and then stretched by a factor of 5. So again, we stretched out by a factor of 5. So what was at 1 is now going to be at 5. And then our whole thing is moved up to 2. We can see that right here with the asymptote, where the asymptote's going up 2. Again, if we want to double check the table, we need to go all the way back a bit. The easiest way to see that we got it right is to see that, yeah, our y1 is at 1. If we multiply 1 by 5, we get 5. 5 plus 2 would be 7. So we can see that that is the right shift. We can see that same relationship holds with 7. And if we go back to where the asymptote is, we can see in the y1s, they're headed towards really small numbers. Those are all effectively 0 or very close to 0. And the y2s round all to 2. So it's kind of cool. So that's how we could do that one if we want to double check ourselves with the TI. Again, I want to show off a TI trick. So that's the TI trick for number 1. Number 2, function models a population of butterflies after X years. What will be the population in 9 years? The goal is we're going to plug 9 in for X. So 5100, 1.065 to the 9th power. And again, if we want to throw this in the calculator, not too bad. Second quit, 5100, 1 point, I always pick the numbers, 065 to the power of 9. And that's going to give us our answer, 8989. That's it. Again, we can round to the nearest butterfly. Makes sense, it's a butterfly. For this function, we need to identify everything. Again, we could just do it by looking at the function itself, but if we want to use the TI, we want to type this into the y equals screen. So -2. Clear that out. Clear that out. -2 parentheses 0.5 to the power of x. All right, and the other part is -3. So if we graph it, we can see most of our pieces. If we hit the trace button right there, we have x equals 0, y equals. So that's going to tell us right away what our y-intercept is going to be. Now, note this is a little bit different than the quiz. And the reason it's a little different than the quiz is because we have this -3. So normally we would say the answer is -2, but we have to do -2 minus 3. For our asymptote, we can see the asymptote down here is headed towards 3. So y equals 3 is the answer because the asymptote must be an equation. So we do need that to be a y equals. The domain for all of these is negative infinity to infinity. And again, if we look at that, we're always going, we can go to the left. This will keep going to the left. This one will keep going to the right. For the range, we're going to start at negative infinity because that's the lowest it goes, but we're not going to go to 0 this time. See how we have it shifted? We're only going to get up to 3. So that's going to be our range. So we're going to go from negative infinity just to negative 3. And again, if we wanted to double check that that was negative 3, we can come up to the table. So second table. We know that the asymptote is to the right, so we're just going to go right a bit. And we can see, okay, yeah, we're definitely headed towards negative 3. So that's what we want to do for that one. Again, totally possible to do without the calculator, but if you want to use the TI, that's what you would look for in the TI. All right, number 4, exponential model that passes through the points 1, 8, and 232. Now, if you want to do it by hand, I think it's a little bit easier to see that this is just times 4 every time. So our answer is just going to be, if we go back to 0, 2, 4 to the x. However, again, if you want to use the TI, that's what we're doing. What we want to do is put these 2 points into the stat menu. So we're going to do stat, press enter to put in our data points. I don't need that one. There we go. Our data points are 1 and 2, and we've got 8 and 32. Not 32. And we can go stat over, and we want to pick the exponential regression. So again, that's not on the screen right now. We have to go down to xreg. We're going to press enter a few times to get the equation to show up, and we can see A is 2, B is 4. Since A is 2 and B is 4, and if we were to plug 2 and 4 in here, we would get the same equation if we did it by hand. But if you want to use the calculator, that's how you can do it in the calculator. All right, for number 5, we have to find the average rate of change from 0 to 4 shown in the graph. This one's just a slope equation, not really anything you can do on the TI except plug the formula in. F of B minus F of A over B minus A. So 5 minus 2 over 4 minus 0, which is going to be 3 over 4. And I'm not even going to turn that into a decimal. 3 over 4 sounds pretty good. Again, what we're doing is we're finding the slope between those. And if we add that line, that imaginary line, 1, 2, 3 down, 1, 2, 3, 4 over. So that makes sense. Oh, wait, negative. Where did we mess up? 4 is 2. Good thing I double checked. These need to be flip-flopped. 2 minus 5, so we get negative 3. Because this should be A, F of A, B, F of B. So there we go. All right, sounds good. Good thing we checked it. Again, the only thing you use the TI for would be to type that into your TI if you want to get a simplified version. Decimal is okay if you do want to give a decimal, as long as it is exact. So if it's 2/3, you cannot give me 0.66666. It has to be 2/3. You can give me 0.6 repeating, that's fine. But I do not want a decimal approximation. Number 6, Warren of rabbits, population 40. We're increasing at a rate of 18% per year. How can we write an exponential growth function to find the monthly growth rate? So we know we're doing exponential growth. So the exponential growth function is y equals a times b to the x, where we know that in this case, for growth, we're going to add, all right, we have 18. We're going to add to 1. A is going to be the starting rabbits, so we have 40 rabbits to start with, and that's going to be our final answer. So that's all we want to do for that one. We want to recognize that growth means we want the plus sign. All right. For 7, what's the inverse of the exponential function y equals 9 to the x? So the idea with inverse, we switch the x and the y first. So we make this x equals 9 to the y. And then we can use whatever we want in order to actually get the y by itself. So if you want to use log 9 on both sides, we would then say log 9 of x equals y, because log 9 and 9 would cancel, and I'm already done. I'm already by itself. It's already by itself. If you want to use the definition, you'll end up at the same place. If you want to use the snail, just make sure the x is over here, and then we can use the snail as well. Log 9 of x equals y. That's it. Again, nothing to do in the calculator on that one. That one you kind of got to do by hand. For 8, evaluate these to 4 decimal points if necessary. So we can type all these in if we want. The first one, though, log 3 and 3, those would cancel to 1. Log base 2 of 32, I think it's going to be easier to say 2 to some power is 32. And that power is going to have to be 5. Log 15, though, I don't know. So that one I would have to put in the calculator anyway. So let's go ahead and put in the other for the first two just for fun. So log base 3 of 3. So we're going to have to go math, and we have to go down to log base. Remember, if your calculator does not have log base, you have to use the change of base formula. But log base 3 of 3 is 1. If I don't have the log base, to do the second one, we want to do log of the big number. So I think that's log of 32 for the second one. Yeah. Log of 32 over log of 2. So that'll work out. That still gives me 5. That's the same thing as if I put in the log with the little number here. Again, if my calculator doesn't have the log base, I have to do it this way. I know some of the calculators are a little bit old and don't have that. The last one, though, is just log of 15. So we're going to type that in. And we can see this one I do need to round to 4 decimal places. So 1.1761. I do need to round it. So 1.761 is the answer. And wait, 1.1761. I think I double checked again. Catching mistakes. 1.1761. All right. Number 9, what's the solution to this equation? Again, I think it's going to be easier to do it by hand. You can either do 3 to the power of both sides. If you want to use the snail, you can use the snail to do 3 squared equals 2x plus 1. So minus 1 both sides. 3 squared is 9, so 9 minus 1 equals 2x. Divide both sides by 2. 9 minus 1 is 8. 8 divided by 2 is 4. We get 4 equals x. And you can do that if you want to do that 3 to the power of both sides as well. 3 log 3, 2x plus 1 equals 3 to the 2. Those will cancel out. 2x plus 1 equals 3 squared. And we're kind of in the same position. So no matter how you want to do it, you can do it that way. It is an equation. Equations you can solve graphically. So log base 3 of 2x plus 1. So math, let's go down to log base again. Log base 3 of 2x plus 1. And we want that to equal 2. So if we graph it, we can see, all right, I think I see where that intersects. I'm lazy though. I want the calculator to do it for me. So second trace, number 5 for intersect. I want the blue curve. I want the red curve. Tell me the answer. And they do intersect right there at 4. So that's what we got. X equals 4. If you put the y coordinate down, you are wrong. They don't intersect at 2. So they only intersect at 4. There are no y's up here. 4 is the only answer. 4 is the answer that we want to pick. Oops. And as you can see, we got 4 right there. All right, for 10, we have this graph. What's the value of the inverse function at x equals 8? So here the idea is to remember what an inverse function is it means we're going to switch the x and the y. So if I want to know where the inverse function is 8, that's telling me that I want to know what happens or where I'm at right now to get to 8. Well, over here at 8, I'm at 8 comma 1. So 1 goes with 8. So the answer is 1 because I'm finding the value of the inverse at 8. And that's it. That's all we have to do. You could do some stuff to actually get the inverse. If you wanted to go a little bit longer, you could. You could say that this is y equals 4 times 2 to the x. Switch that to x equals 4 times 2 to the y. Divide both sides by 4. Equals 2 to the y. We see we have 2, so we can log base 2 both sides. X over 4 equals y. And then I can plug in the 8. So I can plug the 8 directly into the equation. So if I like the equations better, this is what I would do. Log base 2 of 8 divided by 4 equals y. So log base 2 of 2 equals y. And we know log 2 and 2 would cancel. So we would get 1 equals y. So again, we can get 1 either way. We can either get it with the graph or we can get it with the equations doing the inverses. Both ways work out well. Not really much to do on the TI in this case. I guess you could type in this function if you really wanted to, or if you got to here, you could type that in and figure it out, but there's not really much to do on the graphing calculator. You can type this in, but we already saw how to type in a log. For 11, the log function ln of x is transformed to ln of x plus 4 minus 2. Describe the transforms. So here I see I've got the plus 4 on the inside. That means that we're going to the left 4. I see I've got the minus 2 on the outside. That means we're going down 2. And that's it. That's the full answer. Again, if we want to double check it, ln x and y1. Ln x. Ln x plus 4 minus 2. Then we can graph it. And we can see from the blue curve to the red curve, because if we look again, blue is the original. We can just look at the starting point. So it goes over 4 to the left, and it goes down 2. 1, 2, 3, 4. That looks kind of weird. So let's go ahead and look really quickly at the table. We got to go the other way. So we can see here. Yeah, we can see where our errors start. So here, errors start at 0. Here, our errors start at minus 4. So we do need to go 4 to the left. That graph's a little misleading. I don't know about that one, but that's how you do it. So you can also look at the graphs if you want to look at the graphs. I guess be careful because this does look like it goes below 4. It really doesn't, though. That's just pixels that it has to draw. That's it. 12, find the equation of the inverse. F of x equals log 4x. So again, we're finding the inverse. So to find the inverse, we swap the x and the y. So x equals log of 4y. We have to undo the log. Again, you can use the snail, you can use the definition, or since it's a log, we know a 10 to the power will cancel out the log. So 10 to the x equals 4y. To get y by itself, we'll divide both sides by 4. And that's actually it. We are done right there. So there's nothing else to do. We just have to get the equation. Since we're just getting the equation, you probably aren't going to use the TI for anything there. We don't divide 10 and 4 because, again, exponents have to happen first before you can do division for order of operations. 13, expand the expression. Again, we're probably not using the graphing calculator on this one, but we just want to follow all of our rules. So first rule, we want to go ahead and undo our multiplication. So we'll do ln of x squared plus ln of y over z to the third, because that's our multiplication. Next, we want to undo this division. So ln x squared plus ln y minus ln z to the third. Let me make little notes here. I'm turning multiplication into addition, and here I'm turning division into subtraction. Third rule was we wanted to turn all the exponents into coefficients, so exponents to multiply. So 2 ln x, there's nothing on y, so we leave that as ln y, minus 3 ln z, so exponents to coefficients, or exponents to multiplication. We could simplify. There's nothing to simplify, so this is our final answer. Right there. Simplify, but there's nothing to simplify. That's it. Again, not really much we can do. I guess if you really wanted to pick numbers for x, y, and z and try those in the calculator, you could, but I think that's a little bit more work than is worth it. 14, use the properties to condense to a single logarithm. So we're using those same properties, but backwards. So here I see I've got all these numbers out front, so they're all going to become exponents. So log of 2 to the 3 plus log of a to the 4 minus log of b to the 2nd. So again, since we're going backwards, our coefficients or our multiplication became exponents. Going backwards, I see I've got a minus sign, so we're going to go ahead and change that up. Log 2 to the 3rd plus log. So this minus sign is going to become a division. So a to the 4th divided by b squared. Remember, we're condensing things. We want to get to a single logarithm, so we should be removing logarithms at this step. So this is going to be a subtraction to division. And again, once you get past the first step, the goal is to make less logs. So I've got 2 logs here instead of 3 logs. Oops, black will be next. I use purple. So then what we want to do is see we've got addition. So we're going to turn that into multiplication. So log 2 to the 3 times a to the 4 over b to the 2nd. And again, we did addition to multiplication. Now we got only 1 log left. That's really good. Last step we can do is we can simplify. Here we are expected to simplify because we just have 2 to the 3rd. So 2 to the 3rd is 8, so we definitely want to just turn that into an 8. So 8a to the 4th over b squared. And that's my final answer. Where would I use the calculator? Maybe on the last step if I wanted just to double check what 2 to the 3rd power was. When I'm simplifying, I could simplify in the calculator and I can see, okay, yeah, that 2 to the 3rd should probably change to an 8. All right, 15, solve the equation for x. Now it says give the exact solution as a logarithm and approximate the solution to the nearest thousandth. So that means that we can't just use the calculator. We have to do it by hand first because we have to give the exact solution as a logarithm. You can use your favorite solving method, whether it's log both sides, definition, or the snail. Log base 4. Of 11 equals x, and that's actually it. That's what we want to do for the exact solution. So notice it says as a logarithm, I have a logarithm as my answer. Approximate to the nearest thousandth. Again, this is where we're just going to type it in. Let's go down to log base 4 and 11. And we get 1.7297. Remember, if you don't have the log base, you can do log of the inner number divided by log of the base. And you'll get the same answer, 1.7297. Where do we have to go to? The nearest thousandth. So that's 10th, 100th, thousandth. So this rounds this up to 10, which means we're going to go 1.730. So just like in science class, it says it's to the nearest thousandth, so that's like 3 sig figs. So we have to do 3 after the decimal point. So that's it. That's 15's done. 16 looks like it's the exact same. All right, well, let's do it the exact same way. So 5 to the 2nd. Oops, that's again. I keep going that way. Log base 5 of 2 equals x. Approximate the solution to the nearest thousandth. We can do that. .4306 to the nearest thousandth, 0.431. All right, kind of cool. So you might ask, well, what's the difference between these two? Oh, well, this one, the base was smaller than the answer, so we got a number that's bigger than 1. Here, the base is bigger than the number, so we get an answer that's less than 1. So kind of cool. All right, fair enough. 17, solve the equation by using a common base. The instructions say by using a common base. If you do not use a common base, you do not get this answer correct. You cannot score any credit if you do not use a common base. Doesn't say just regular solve. You can use regular solving techniques to check, but it does say to use a common base, so you must use a common base. So in this case, 3 doesn't really break down into anything. 3 is just 3. We can't make 3 like 7 times 8. But 9, we actually can change. We can change 9 into 3 squared. So we got 3 squared x minus 2 equals 3 to the x plus 2. At this point, I have a common base, so I can write down the answer from here if I want to solve it in a different method. You do not need to continue the way that I'm going to do it. I'll show you how to do it with the graph in a little bit. But I need to have this down on paper in order to score credit for this question, because it does specifically say to use a common base. We saw in class that if we have power to a power, we're going to multiply. So we're going to multiply this to each of those pieces. So 3 to the 2x minus 4 equals 3 to the x plus 2. And again, the 3's will cancel out. You could do log 3 both sides. You could use the property that since the bases are the same, the exponents must be the same. No matter what the result is, we're going to rewrite this as 2x minus 4 equals x plus 2. We're going to get all the x's on one side. X minus 4 equals 2. We're going to add 4 to both sides. So x equals 6. And I'm pretty happy. I'm going to use my check with the calculator, but remember when we do these ones with the exponentials, you don't need to double check them because the domain for all the exponentials is negative infinity to infinity. There's no extraneous ones with these ones. If I want to double check it, I'm not going to put the original in because again, I'm focused on changing the base. I could, but I'm going to put this in because I have to get here no matter what. So I'm going to do 3 squared to the x minus 2 power. So 3, do that in parentheses, 3 squared to the x minus 2 power. I can't put in an x, and everything went away again. That's all right. 3 squared to the x minus 2th power on one side, and then on the other side, I've got 3 to the x plus 2th power. Keep doing x. All right, so if I graph these, as we can see, I'm not quite sure. So it looks like they're going to connect down here, but remember, those are the asymptotes. That's probably not where the answer is. Even though I can't see it, you know what? Find the intersection for me, calculator. First curve blue, second curve red. Do I get them to connect? I do. Like they connect at 6. So I'm happy I got the right answer. Even though I can't see it, I'm going to trust. If you don't trust, we can come to the table. And this time it's a little bit easier to use the table rather than zooming out. We can see that the two y values are the same there. So since those two y values are the same, that's definitely where they cross. So there we go. So we get x equals 6. All right, for 18, find all solutions to this equation, label extraneous solutions. So this time it does not say that you have to find a common base or anything. So you can just put this in the calculator and solve it graphically if you want. Obviously, it's more fun to do it by hand. So what we're going to do is take this 2 as an exponent or as a coefficient and use my ln rule to turn that into ln of x squared. This way I have ln of both sides. Again, I can cancel out the ln's. I can do e to the power of both sides. Or by definition, x plus 2 must equal x squared. And now I see I've got a regular quadratic. So I'm going to minus x and minus 2. So 0 equals x squared minus x minus 2. I can factor it. X minus 2, x plus 1. I can solve it with the zero product property, x equals 2, x equals negative 1, and that's going to be my two answers. But, like we said, we got to double check them because now we have logarithms. If we have the logarithms, we need to double check to see if anything is extraneous. So ln of 2 plus 2 equals 2 ln of 2. So ln of 4 equals 2 ln of 2. Nothing is wrong in the domains, so we're good to go. Yeah, we can type it in just to double check the decimals. quit. So ln of 4 to ln of 2. We get the same decimal, so that seems pretty good. If I try the other one, let's go ahead and give that one the check. ln of -1 plus 2 equals 2 ln of -1. So this is ln of 1 equals 2 ln -1. And I'm going to X that one out because I know I can't put a negative inside the log. If I do want to double check with the calculator, I still could. So if I forgot, or if I just wanted to double check, ln of 1 is 0. 2 ln of -1 is a non-real answer. So we can see we're outside of the domain. So we're going to quit, say, oh well, didn't work out. So just in case, let's just double check to see if anybody's calculator is in strange mode. We'll go into imaginary mode real quick. Just see if we get an imaginary answer. So we do get an imaginary answer. So if you did put your calculator into imaginary mode from that time when you did all the stuff with the eyes, you will get an answer. It will have an I. You don't want an I, so obviously that would then be the one that you don't pick because 0 does not equal 6.28 I. Like that just doesn't work out. Very cool number though, 6.28. Is it? It's looking very suspicious. It is 2 pi, so it turns out that that's 2 pi I. Kind of cool, but yeah, we're kind of getting off track at this point. Let's switch back into no eyes please mode. That's no real mode for no eyes. And let's carry on. So for 19, solve the equation. Oh wait, no, we gotta go back. I gotta show you how to do it with a graph. I almost forgot. ln of x plus 2. I almost forgot to graph it. ln of x plus 2 and 2 ln of x. That would have been bad. So we can graph it, and we can see that they do connect right here. That definitely looks like 2. Again, if we do not trust the calculator, we find the intersect. I want the blue curve. The red curve, I can't press enter yet because we can see there's no y equals, so I got to go over a little bit to get on the red curve. And then tell me the answer. Yeah, the answer is 2. Okay, sounds good. And look, it's that decimal that we got when we tested out to see if they actually matched up. Cool. All right, so pretty good with that one. All right, number 19 then. So solve the equation log base 3 of 2x equals x by graphing. So here it specifically says by graphing. So we do not want to do any work on this one. We just want to go ahead and put it into the graphing calculator and figure it out. Round to the nearest thousandth. I mean, we'll do that when we get to it. So log base 3 of 2x. So up here, we'll do log base 3 of 2x. And then in the other one, we want to make this equal to just x. Okay, that's nice. All right, so we can graph it. Whoa, wait a second. Those two don't look like they touch. Could this be a no solutioner? It might be a no solutioner. So let's see. Calculate the intersect for me, calculator. First curve. I can see again, I'm not on the blue curve yet. So let's go over to get on the blue curve. Second curve, red. Answer, no sign change. So no sign change means they don't actually connect. That's a little disappointing. All right, well, guess we're done. No solution. It happens sometimes. Oh well. All right, let's quit out of that. Just to show you that if you didn't have the log base, remember we can type this in as log of 2x. Divide by log of 3. And again, we get the same picture. If we want to make this, if we want to force this to actually have a solution, let's change this x to, I don't know, x minus 5. This way now we can see, oh, they do connect. So just to prove that what we did actually will work, we can find the intersection. Blue curve, we got to get on the blue curve. We're on the red curve. Tell me the answer. The answer here is 0.002. So wait, is it? Oh, that's one of the answers. Because remember, this goes like that. So that's one of the answers. We're actually going to get two answers. I was expecting it to go over here, but it went right there. Huh. But that, again, that makes sense because remember, this blue curve will kind of asymptote at this x equals 0. So it should connect somewhere over there. Second calc, 5. Give me a better intersection. First curve blue. I'm not in the blue yet. There we go. First curve blue, second curve red. This looks like 1, 2, 3, 4, 5, 6, 7. That looks close to 7. So let's guess 7. And then that's the one that's closer to 7. So that's how you can force it to pick this one instead of the one that was over here. 7.460 would be the other answer there. So that one would have two answers. It would actually hit twice. Kind of nice. And that's why it does say answers, because it is possible to get two. All right. Last one, right? Yeah. What is the solution to 3 to the x minus 1 equals 2 to the x? Honestly, we're probably going to solve this by graphing. So 3 to the x minus 1 e to the power of, I'm not going to get tricked. I'm not going to type x this time. X minus 1. And then I think it was 2 to the x. It is 2 to the x. 2 to the power of x. All right, so again, we just need to see where these cross. Okay, that looks like they're going to cross right there. So calculator, tell me the answer. Number 5 for intersection. First curve blue, second curve red. Tell me what the answer is. 2.7095. Where do we have to round to? It doesn't say to round, so wait a second. 2.7095113 isn't the answer. Uh-oh, we might be in trouble. Because it doesn't ask for an approximation. We actually have to give an exact answer. We actually can't use the calculator. All right, well, at least we know what we're aiming for. We're trying to get something that's close to this if we do approximate it. So let's give it a go. So in this case, the goal is to try and get this x minus 1 to just be by itself. So let's go ahead and we have to get rid of this 3. So we're going to do log base 3 of both sides. So log base 3, 3 to the x minus 1 equals log base 3 of 2 to the x. So log 3 and 3 will cancel, so that's nice. So x minus 1 equals log base 3 of 2 to the x. And now what I'm going to do is I'm going to use the property that says I'm allowed to take my exponent and bring it out front. X minus 1 equals x log base 3 of 2. All right, so this is some number. So again, we don't really know what that number is, but just be aware it's just a number. It would be the same thing as if this was like 5. Now, if this were a 5, what I would do, again, is I would subtract x on both sides to get -1 equals, and we would normally combine these as like terms. We're doing that here too. Log base 3 of 2 minus 1. Because again, we could, you know what, let's write it all out. Let's write it out before we do this. We'll go slow. So x log base 3 of 2 minus x. So what we're doing is a GCF. So since these both have x, we'll GCF out that x log base 3 of 2 minus 1. Because if we were to distribute, x times log base 3 of 2 is x log base 3 of 2. X times 1 is x. Now again, if this was like a number, if this whole thing in parentheses was a 5, next thing we would do is we would just divide by that number. And we're going to do the same thing here. We're going to divide by log base 3 of 2 minus 1 on both sides. Log base 3 of 2 minus 1. And that's going to cancel these out. So that's going to give me -1 over log base 3 of 2 minus 1 equals x. And then I ask myself the question, is x by itself? The answer is yes. So the answer is this. This is actually the answer. That looks very odd. So let's go ahead and say, all right, well, we're going for something that's like 2.71. Let's see if that's close to 2.71. Negative 1 over log base. Let's do the fraction. So log base, oops, negative 1's up top. Negative 1 over log base. Scroll down to log base. 3 of 2 minus 1. It's the same decimal. So that's it. That's actually the answer. All right, pretty cool. So kind of fun. That's a nice little fun algebra one. So it kind of reminisces our old days in algebra one where we were doing kind of the literal equations. We were trying to get the x by itself and we didn't really simplify much. But that's it. That's what we're going to do. And that's the end. So that's everything. And that's how to use the TI to kind of check some of the answers or to make sure that you're kind of close to some of the answers. And so that's it. So cool.